discussed the concept of the standard error of the mean. And I told you this is, you can calculate the standard error of the mean just by using the equation standard deviation divided by the square root of the observation that you have. Bless you. And let's say we have a sample where we have an average. This x bar is 55 whatever, 55 centimeters or God, yeah. We have a standard deviation which is, say, 10 centimeters, and our sample contained, say, 16 observations. Now we can very easily calculate the standard error of the mean in this case. So in this case, the standard error of the mean, and you will see it as SEM or SEX bar. Sometimes you even see SEY bar. Why? I don't know. So all we need to do is put in our numbers. So we have 10 centimeters divided by square root of 16. This gives us 10 centimeters divided by 4, and that gives us 2.5 centimeters. So we can say, we can report back that for this particular sample, we found a mean of 55 centimeter with a standard error of the mean of 2.5 centimeters. And this just simply is another measure. The standard error of the mean is just another way. Oh, I thought it was my heartbeat. It's just another way of indicating that there is a certain variability within the data that we find. So it's another means of or measure of dispersion. Measure of dispersion. But we can do something with the standard error of the mean. And I talked a little bit about what is called the confidence interval. The confidence interval and this confidence interval basically indicates in what range the true population mean lies. Remember, we have a population but we can't measure the entire population for whatever reasons. So we take a little sample of that. So that's our sample. And from this sample, we try to figure out, we use the sample to figure out the parameters of the population. So this sample, up to a certain point, should tell us what is the population mean and what is the spread within this population, what is the standard deviation. And it would be very dangerous to say, you know, our sample that's the sample mean. If we measure the heights of students, let's say, is, say, 178 centimeter. That's our sample mean here. Now, it would be very, very almost idiotic to say, because our sample mean is 178 centimeters, I therefore conclude that the average of all the students is 178 centimeters. But what can I do instead? What statisticians usually do instead, they say, right, from this sample mean and the associated standard deviation, I can define a certain range. Can define a range in which the population mean can be found. So I can say, right, I have 178 as my average sample mean. So I assume with a certain degree of certainty that the population mean is probably, or I should write this in a different way, is between, say, 165 and 183 centimeters. So instead of saying this is the population mean, which is very dangerous to do because I'll almost certainly be wrong with that, I can say, I guess that the average of all the students on campus lies between 165 and 183 centimeters. That is this range. And of course, if I make this range very big, if I say the average height of all the students on campus is between 40 centimeters and 310 centimeters, I would be probably pretty much, this would span my range that where my population mean is, but it doesn't tell me a lot. On the other hand, so if this range is too big, range too big, who cares? Doesn't tell me anything. If I make the range too small, so if I say, for example, I believe strongly that the average height of all the students on campus is between 175.1 centimeter and 175.3 centimeters. And this is very precise, but I'm probably wrong. Most likely wrong. So I have to choose this range in such a way that it tells me something and that I'm fairly certain that I'm right. Yeah? And we can do this to calculate this confidence interval, to calculate this range. We can say this is the sample mean that we have plus minus what I call the fudge factor, which the proper name is t. This is the t factor times the standard error of the mean. And here it is again. Yoo-hoo! We have our little SEM back. So what does that mean, actually? Let's just quickly do a little calculation. Let's say we have the height of our students, and we take a very small sample. So let's say I measure only 3 students. And the average of these 3 students is, say, 175 centimeters. I can also easily calculate the standard deviation. And let's say the standard deviation is 17 centimeters. And you all know how we calculate the standard deviation. I've showed you, and I also showed you how you can do that in Excel. It's a sample, so we measure the squares of the differences divided by n minus 1, because it's a sample. And then take the square root of that. So what can we do with that? Can we, from these 2 data, can we say with some confidence, with some certainty, what the average height of all the students on campus is? That is actually what this confidence interval tells us. So, we have the confidence interval, x bar, that's 175 centimeters, plus minus this t factor, times, and now we need to do the standard error of the mean. And if we go back, I showed you here what the standard error of the mean is. So standard deviation divided by the square root of the samples. So standard deviation, that is 17 centimeters, divided by the square root of the observations that we have, that is square root 3. What do you get for the standard error of the mean? 9.81. Yep. So that is 175 centimeters plus minus t times, shall we say 10? It's easier to do 10 centimeters. Yeah? So what we now need is this flaming T. And I told you this T is not a fixed number. This T depends on a number of things. It depends on how certain I want to be. So it depends on the certainty. And usually I want to be 95% sure. So that's usually set to 95%. And it also depends on the sample size. This is what this t depends on. And in the case of 3, if we have a sample size of 3, and if we want to be 95% sure about what we are doing, then this t, and I don't expect you to remember that. You're not supposed to learn t-values by heart, so don't worry about that. I will always give you a t-value. Yeah? But I'll show you in a minute how you find it out yourself, because I figured it out on Excel, how to do it. So t, in this case, would be 4.3. But t changes. The larger our sample size, the smaller t. So what I can now say is, with this I can calculate my confidence interval. So let me write this down again. Confidence interval was 175 centimeter plus minus 4.3, that's the t-value, times 10 centimeters. Yeah? This is now my confidence interval. And I can say, with really pretty good certainty, I know that the average height of all the students lies between 175 minus 43 centimeters, so that's 43 centimeters here, and 175 plus 43 centimeters. So that would give me 132, and that would give me 218. So I can say this confidence interval allows me to predict that the true height of all the students is between 132 centimeters and 218 centimeters. Where exactly it lies, I don't know. But I know that it is fairly certain, not 100% certain, but it's fairly certain that it is between this range here. Yeah? That is what this confidence interval tells me. Now, I can go away and do the same thing for, let's take an example that you're probably completely unfamiliar with, just out of fun. Let's say we want to determine the sugar concentration in honey. Yeah? Just for fun. And I can do exactly the same thing. So I can measure my sugar concentration in honey, and I just make up something here. Let's say glucose concentration in honey. Honey is, let's say, 30, I measured it, 30% weight per volume. Yeah? Is that a reasonable value? Something along that line? Yeah. So, this is my measurement. So my X bar, and I did this experiment in triplicates. Did you do it in triplicates? Or just once? You had different honey amounts in, okay. So you could do that basically in triplicates, yeah? So you measured 3 different samples. And you got 30% weight per volume of glucose. And you even, if you did it in triplicates, you could have done a sort of a standard deviation. Yeah? You could perhaps found is 1% weight per volume. That would be, I just make up some data, but that would be your standard deviation in this case. Now, what is your true concentration of glucose in the honey? Is it 30%? What do you reckon? Is it 30%? It's not. Why not? It could be around the 30, yeah? It's probably a pretty good guess that the true concentration in this honey is around the 30, but we can't be 100% sure. So it's better to say our true concentration of the honey is in a certain range. And with this range, to find this range, again, we do our confidence interval. So confidence interval. We say X bar plus minus the fudge factor times S divided by the number of observations. And if I did the experiment in triplicates, I have n equals 3. So I have 30% plus minus the t for sample size of 3 with 95% is 4.3 again times 1 divided by square root of 3. Yeah? And if you calculate that here, 4.3 times 1 divided by square root of 3, you get, let me do that, 2.48. Is that right? Yeah? Are you impressed that I can do that in my head? I'll tell you the trick later. Or let's do it 2.5 is easier. So we know that the true concentration of our honey is most likely between 27.5% and 32.5%. Have I made a mistake? So in this range, there is most likely my true concentration. And I believe this one here, this 30%, that is sort of in the middle, that is the mean that I find. Yeah? So the true concentration of the honey is in this range. And I'm pretty sure that this is the case, 95%. Are we happy with that? And all I need to do in this case is I really only need the standard deviation, I need the sample size, and I need this t. And to find this t value, generations of students before had to use weird and wonderful tables where they had to look up the t value. Now, luckily, we have computer programs that can calculate that, and I played around with Excel, and the function that you need to calculate the t value is in Excel, as I discovered, which is different from the Mac version, is t.inv.2t. Who came up with that should be crucified by the ears, because nobody can remember that. And then you put in, and again, whoever came up with that should be shot. You put in not how sure you want to be, you put in how unsure you want to be. Exactly. This is my thing. So, if you want to be 95% sure, it means you are 5% unsure. And therefore, you put in 0.05. And then you also need the sample size, and you put in n minus 1. There is, luckily, if you are a scientist working in the lab, there's a little shortcut for that. Luckily. I call it PK's shortcut, because I've never seen anyone doing anything like that and calculating the data beforehand. What you can do, very simply, is if you have, and it only works with data in triplicate. So only with data in triplicates. If you do more or less, it doesn't work. But in this case, the confidence interval is your mean plus or minus 2.5 times the standard deviation. That's my shortcut. And this 2.5, that is sort of a constant here. You don't have to figure out a t-value or anything like that. 2.5 times the standard deviation, that gives you the confidence interval here. It's quite handy, because I can immediately, if somebody says, I have sample mean and I have that standard deviation, I can immediately do the calculation in my head and say, okay, your confidence interval is this. And these confidence intervals can be quite handy if we want to represent data, because what we very often want to do is we want to compare data. So what we usually do is we have our data set, something like that, with drug, without drug, with more drug, things like that. And I want to make sure that I show these error bars which indicates to the reader, there is that amount of uncertainty. Very often, confidence intervals are quite good error bars. So we could do it something like that. We could do something like that. We could have an error bar like that. And these are basically from the confidence intervals. So that would be here, this point plus, and this point minus here. That's the upper bound, and that is the lower bound. Okay? And with this confidence interval for each one of them, I can say, oh, that's interesting. What would happen, for example, if I had a sample, say, here, with this confidence interval? So I have this one here. And I compare that to all the other samples that I have. What does that indicate? In the case of this, in this case here, the confidence intervals don't overlap. So there's no overlap between the confidence intervals. And that indicates to me that the mean of this population here and the other means for this population here, that they are different. But we come back to that on Monday, what this actually truly means. Does that make sense so far? Yeah? You can calculate confidence intervals? Yeah? Excellent. Now, what I want to do with you now is I want to present you with a little challenge. We talked about glucose in honey. And this is our honey pot. That's the population of the honey that was in the lab, basically. And let's say John took a sample, 3 data, and he found that the average is the X bar found it's 30% weight per volume. Okay? Now, Tiffany did exactly the same experiment. She also took 3 data, let's say here, 3 data, And she found that the glucose concentration is 28%. Who's right? John or Tiffany? Sorry? Say loud. Yes. No? Who is right? It's different experiments. Well, but they are all from the same population, aren't they? Or there are different problems in it. Errors? Wow. Okay. We need an arbiter, a referee. Gabriel did the same experiment, 3 data, got 32%. Who's right now? All of them. Actually, I like your thinking. Even if we assume that there are no human errors, it could be that there are differences in the honey, for example. They all belong, everybody took from the same honey pot, but there were slight differences in it. And these differences are reflected in the different means. So, for example, I can say that was mean 1, mean 2, mean 3. The samples still reflect the same population. All samples belong to the same population, but they are slightly different. So they're slightly different. Maybe another experiment would be, again, I want to measure the height of students. I take 3 students over there, measure their height, 180 centimeters. Then I measure 3 students over there, 175 centimeters. So the samples would be different. Right? And if they are different, then people might say, oh, well, you made an error. But actually, if the samples are different, but still represent the same, population, then this is called sampling error. It sounds horrible. If somebody said to me, you made an error, this is a criticism, isn't it? You're dumb. But in this case, it's not an error that I made. It is just simply because I take samples, and these samples are different from each other. There's nothing I can do. So the sampling error is always there. Whenever we take samples, there is a sampling error. And there's nothing on Earth that can be done to avoid this sampling error. What I now can do is I can say, right, I know that John had a mean of, say, 30%, and Tiffany had a mean of 28%. And I know that there is inherently a sampling error. I can't do anything about it. But I can ask, are these two means different? Of course the means are different, but why are they different? Is it because they are different, they are truly different, or is it because of this damn sampling error? I know that the sampling error is there, so I would not expect the means the same. Because the sampling error is there, my means must be different. I know that. But how different is different? So I can basically ask this question. Are the two means different? And is this difference caused only by the sampling error? Or are these two means different, which is caused by the sampling error and something else? Maybe John and Tiffany use different honeys. Yeah? So, I can ask the question, or I can make a statement. The mean of sample 1 is the same as mean of sample 2. And I say, there is no difference between the two sample means other than caused by the sampling error. I can't get rid of the sampling error. That's always there. Yeah? That is one statement. And this statement, actually, I want you to learn this. I don't usually ask people to do that. But in this case, I want you to learn this statement by heart. And this statement has a name. This statement is called the null hypothesis. And we usually abbreviate that by H subscript 0. That is the null hypothesis. Our two means are the same apart from the sampling error. I can come up with an alternative hypothesis. Good morning. I'm done in a minute. We can come up with an alternative hypothesis. The alternative hypothesis and we would call that H1 is the two means are not the same. The two sample means are different due to two effects. We always, again, have the sampling error. Due to sampling error and another effect and another reason. This could be, in our case, that we took two different honey pots, two different kinds of honey. So, again, I would like you to remember that the null hypothesis and the alternative hypothesis. And on Monday, I show you how we can test our null hypothesis. What we can do, actually, to find out whether the samples are the same or whether, and the difference that we see are just simply due to sampling error, or whether the samples are truly different, sampling error and something else. Don't forget to do your homework, and have a lovely weekend.